Okay, in this question we're asked to compute the derivative of the product of these three functions. So you could either remember a sort of triple product rule, f, g, h prime is the same as you just differentiate one at a time, leaving the other two fixed, and add the results. Or you could apply the product rule twice, where you think of this entire guy as an object. So that what you would do is, you would think of it as f times g times h, collectively prime, is equal to f prime times g times h, plus f times g times h prime, and then you would use the product rule on that. This would just be f prime gh, that doesn't change. But then here the product rule on this is f times the quantity g prime h plus g h prime. So then you would distribute and you'd get f prime gh plus f g prime h plus f g h prime, just distributing the f here, which amounts to the same formula here. So either way, this is the game you play when you're multiplying three things. So we have to take the derivative of each of these guys. So the derivative of x is easy, it's just 1. So the first term is e to the negative x squared cosine of x. What are we adding on? We're adding x times the derivative of this monster. And then we're going to multiply by cos x at the end. But what is the derivative of e to the negative x squared? Well, by the chain rule, there's an e there. So it's the derivative of e to the x is just e to the x, but you plug in the inside function, so it's still e to the negative x squared. But now we have to multiply by the derivative of whatever's on the inside, whatever's in the exponent, which is negative x squared. So we should also be multiplying by negative 2x, because that's the derivative of negative x squared. And let's not forget to add on, to tack on a cosine of x there. Okay. And then finally, we would be adding on the derivative of cosine. But the derivative of cosine is just negative sine. So this is x e to the negative x squared times negative sine. So this should have been a relatively easy problem. The next problem is going to be a bit more challenging. Switch over to blue here. You're asked to compute the arc sine of x over the arc cosine of x. And in case that wasn't hard enough, let's cube the x on the inside in each case. Now how do you find the derivative of that? Well, you'll notice that in order to compute the derivative of arc sine of x cubed, you'd have to use the chain rule because you're cubing the inside, and the same thing goes for the arc cosine. So we're going to use the chain rule. Of course, we have an overarching quotient, so we're also probably going to use the quotient rule as well. And finally, do you remember the derivative of arc sine and arc cos? No, probably not, so you might have to think about what the derivative of these inverse trig functions are. So we have a lot of problems that are all wrapped up into this one derivative problem. So we have to take it one step at a time and be careful. But before we do, I want to make a very important point. Arc sine over arc cosine is not the same thing as arc tan. That does not work. It's an invalid statement between these functions. So you can't just simplify that to arc tan necessarily. We are going to have to make things a little bit more complicated than that. Alright, so the first thing I'd like to know before anything else is what are the derivatives of arc sine and arc cosine, just so I get all my ducks in a row. So remember the trick here is you take sine of the arc sine, which from now on I'm just going to write as sine inverse. It's the same thing, it's just a different notation. Sine of the inverse sine of x is x, it just undoes it. You take the derivative of both sides, and by the quotient rule, this is cos of the inverse sine of x times the derivative of the inverse sine is equal to the derivative of x, which is 1. Or in other words, the derivative in which we're interested in, sine inverse prime, is equal to 1 over the cosine of sine inverse of x. So now we draw our little triangle here. I want to define theta so that it's equal to my inverse trig guy, which is sine inverse of x. Or in other words, sine of theta should equal x. So if this is my theta here, and I make this x and I make this 1, then indeed opposite over hypotenuse is going to come out to x. But that would make, by the Pythagorean formula, this last side 1 minus x squared. You take the square root. So now I want to know what the cosine of that is. cosine of the inverse sine, but the inverse sine is theta, so I'm just interested in the cosine of theta, which is the square root of 1 minus x squared over 1. So this is 1 over the square root of 1 minus x squared. So that's what the derivative of the inverse sine is. So let's leave that in our back pocket for a second and compute the derivative of the inverse cosine, because we need to figure that out too. So again, same game. Cos of the inverse cos of x is just x, and you take the derivative of both sides, you get 1 equal to, the derivative of cos is just negative sine, so this is negative sine cos inverse of x times the derivative in which we're interested in, cos inverse prime. Or in other words, we're interested in cos inverse prime is equal to just dividing negative 1 over, so there's a minus sign that moved over, sine of cos inverse of x. You draw your little triangle, call one of the sides theta, and arrange it so that theta is, now we want the inverse cosine of x, so that cos theta is equal to x. Well, that would work if I had an x here and a 1 there. So again, this would be by Pythagoras, square root of 1 minus x squared, and sine of this amounts to the same thing. So that's equal to negative 1 over the sine of theta, cos inverse of x is theta, which is just the square root of 1 minus x squared. So it looks the same, except there's a minus sign. Alright, so now that we know that, I'll switch over to black here, we can attack the derivative of this guy. By the quotient rule, it's the derivative of the top, which is the derivative of arc sine x cubed, which by the chain rule is the derivative of arc sine applied to x cubed, and the derivative of arc sine is 1 over 1 minus x squared. So, wow, this is going to be a lot to write, but I think it would be better if I actually wrote this all out very carefully. So the derivative of the top, arc sine of x cubed prime times the bottom, arc cos of x cubed minus the derivative of the bottom, arc cos of x cubed prime times just the top, which is just arc sine of x cubed. And we're dividing by arc cos of x cubed quantity squared. Okay, so what are these derivatives here? Well, the derivative of arc sine is 1 over the square root of 1 minus x squared, but we're applying it not to x, we're applying it to x cubed. So this is this 1 over the square root of 1 minus x cubed squared. And then we're not done yet, because we have to multiply by the derivative of the inside, which is 3x squared, times arc cosine of x cubed minus the derivative of arc cos cubed is something very similar, except there's a minus sign, right? So it's going to be minus 1 over the square root of 1 minus, and again we're applying it to x cubed, so this is x cubed squared down there, and by the chain rule times 3x squared. And we're multiplying this by arc sine of x cubed. And we're dividing by this arc cos cubed quantity squared. Arc cos of x cubed, and then quantity is squared like that. Okay, so this is, on the one hand, this is the actual derivative, and maybe there are some ways in which you could actually simplify what this should come out to. For example, we have the same kind of term here, but it's off by a minus sign, and we're subtracting it, so this minus would cancel this minus. Sorry, this minus would cancel this minus over here, and that would turn into a plus. So we could factor out a 3x squared over the square root of 1 minus an x cubed squared, power of a power, the powers multiply, that's just x to the 6th. Square root of that, x to the 6th. And then on top we just have an arc cos plus an arc sine. Arc cos of x cubed plus an arc sine of x cubed divided by arc cos of x cubed quantity squared. And you could move these things around and simplify a little bit further if you want to, but that's more or less what it comes out to. I'm not going to go into that because we have another problem to deal with. I'll switch over to green here. Arctan of e to the x to the 2 plus 1. So we have to figure out, first of all, this is another chain rule problem, but we have to figure out what the derivative of arctan is. So we're going to play the same game. Tan of arctan of x is the same as x. Take the derivative of both sides. What you'll find is, and I'm going to skip some steps, but hopefully you can fill in these yourself. You get that the derivative of arctan is 1 over secant squared of the arctan. You draw your little triangle. There's theta, which is your arctan, or your inverse tan of x, so that the tan of theta should equal x. So that means if we make this x, this 1, we're forced by Pythagoras for this to be 1 plus x squared, or the square root of 1 plus x squared. And so the secant is 1 over this squared. I'm sorry, it's that would have been the cosine. The secant is this divided by this squared. So I think when you actually plug that into the sec squared, that comes out to 1 over 1 plus x squared. This is also a very common one that you might just remember. The derivative of arctan is 1 over 1 plus x squared. So if we apply the chain rule, this is 1 over 1 plus the square of, well, we're not plugging in x, we're plugging in this entire monstrosity. E to the x squared plus 1 quantity squared. And then we multiply by the derivative of the inside, which looks like e to the x squared by the chain rule times the derivative of the inside comes out to 2x. So you might be able to simplify this sum if you liked, but that's more or less what it should come out to.